Okay, so the general consensus is that there are three main types of black holes. We've got the primordial black holes, which are super tiny and early universe objects, the stellar black holes, which come from a collapsed star that is like way bigger than the size of the sun, and then the supermassive black holes, which are the largest black holes that we observe in the universe. But what you might not know is that there are two emerging new classes of black holes, namely the intermediate mass black holes, which we don't have any confirmed sightings yet, but there are a couple candidates, which would bridge the gap between the stellar mass black holes and the supermassive black holes. But also the main topic of today, which is the ultramassive black hole class. So I think the last time I mentioned black holes of this size, apart from my How Do Black Holes Grow video, was actually an entire degree away in a blog post that I wrote a couple years ago. So I think my knowledge is a lot better than it was back then on black holes and black hole growth, so I think this will be the perfect topic to tackle today. So let's start off by having a discussion about supermassive black holes, and then we can build up on that and talk about ultramassive black holes. So by definition, supermassive black holes are at least 100,000 solar masses, so 100,000 times larger than the Sun. In standard form, this would be 10 to the 5 solar masses. We expect that they reside in the centres of pretty much most galaxies in the universe, with the exception of course, some very peculiar dwarf galaxies and irregular galaxies. Now, while 100,000 is the lower limit, they can of course grow way bigger than that, and generally speaking, I think most supermassive black holes we see tend to be in the millions to billions of solar masses. Looking into our own galaxy, the Milky Way, the supermassive black hole that resides in the centre of our galaxy is Sagittarius A star, and it's actually quite a small supermassive black hole compared to a lot of the other ones that we see. It has a mass of only about 4.3 million solar masses, which is quite huge on like a human scale, but yeah, in terms of other galaxies, it's quite tiny. I did some back-of-the-hand calculations to look at how big Sagittarius A star would be in terms of its Schwarzschild radius, which is basically where the event horizon is, the distance from the event horizon and the centre of the black hole, the singularity, which we tend to define as just how big the black hole is, because that's when we stop seeing what's going on between there. And I think it was only about 25 million kilometres, basically less than half the distance between the Sun and Mercury. So that's just like a flavour of how compact a black hole can be, because we've got basically 4.3 million times the Sun's mass just enclosed within this really, really tiny space. So it's just super gravitationally dense. So like I said about Sagittarius A star being quite a relatively small black hole, if we just look at one of our nearest neighbours, the Andromeda Galaxy, its supermassive black hole is roughly about an order of magnitude higher in its mass compared to the Milky Way's one. That just goes to show like how small it is compared to all the other ones. And in general, like, yeah, it is quite a small black hole, even if we look at, you know, other nearer galaxies as well. If I remember correctly, I think it's Messier 32, which is Andromeda's satellite dwarf galaxy, or one of them at least, has a mass of about 3 million solar masses. So this dwarf galaxy is like only just slightly smaller than Sagittarius A star, which is kind of embarrassing if I'm going to be honest. And I do know there is another dwarf galaxy which has a slightly higher supermassive black hole compared to Sagittarius A star, but the name is actually escaping me. I think it's Ultra Compact Dwarf 60, or maybe Ultra Compact Dwarf 61. I really can't remember. But I think the main takeaway here is that, yeah, we have quite a small supermassive black hole. An important caveat to note here that I don't think gets talked about enough is that supermassive black hole mass estimation, so figuring out how heavy it is actually ridiculously difficult to do with certainty. And with certainty is the main thing that I want to talk about here. The problem is that black hole masses and like understanding how big they are with relation to other stuff is, you know, just based on models. And a lot of mass estimates tend to be based on models of other models, which are of other models. And in general, we tend to infer the mass indirectly from other properties around the black hole. For example, with active galaxies, we've got this really like dense, fast moving gas that is very close to the black hole, which isn't part of the accretion disk, but is just slightly further out, called the broadline region. And we've also got the narrowline region, which is just slightly further out still, and is usually the bit of gas that we can observe the best compared to the broadline region. We can make some inferences based on those two things because they have a very unique spectra as well. Broadline region produces very broad lines, which tells us how fast the gas is moving, and from that we can well, indirectly estimate the black hole's mass. But in general as well, the luminosity of that borderline region comes from another bit of estimation that you have to do. So you can kind of see, like, if you've got an error, like a big uncertainty in this area and then a big uncertainty in this area, and you just keep on stacking up those uncertainties, you tend to get a very, like, wide range of black hole masses that you can have for this specific galaxy's black hole. And so that makes the uncertainty pretty big. So it is very heavily dependent on models and whether we can get that correct. To be honest, if you'd like a video on like how we estimate black hole masses, I'd be happy to do one, because part of my third year research project was actually estimating some active galaxy masses, which was done through just continuum fitting. But there are many more ways of doing it, such as like broadline fitting or like reverberation mapping. But you can do reverberation mapping for, you know, the broadline region and for like some specific areas that release X-rays as well, which, you know, I know somebody who like does research on that and is pretty cool, but like, oh my goodness, that is an insane area of physics to study. But yeah, I would love to make a video on that, and I'll have to do that sometime soon as well. Finally, my last talking point on supermassive black holes is actually going back to stellar mass black holes. And of course we know that stellar mass black holes form from the collapse of a really large star, or potentially the merging of two compact objects or two like fairly heavy stars as well, which will then bring up the mass enough for it to collapse down to a black hole. But of course, those kinds of stellar mass black holes tend to be, you know, dozens of times larger than the sun, up to even 100 times. But then supermassive black holes are over here in the hundreds of thousands to millions to even billions of solar masses. So there's a really big jump here, and that's kind of an important point as well, because the general consensus is that these stellar mass black holes should then go on to accrete matter and form an accretion disk, which will then help them grow up into the supermassive black holes. So while we don't know if this is actually true, and if it were true, we should see some intermediate mass black holes, but we haven't seen many yet, or at least we haven't confirmed any so far, which is another whole question which we won't get into today. That does imply here that the supermassive black hole sort of class is more of a mechanistic one than just sort of arbitrary. This is going to be an important talking point with ultramass black holes because they don't really have a very solid definition. So let's finally get on to the crux of the video, the ultramassive black holes. These tend to be tens of billions times larger than the sun. They're essentially like an elite club of the supermassive black holes, so the most massive ones that we have seen so far. So similarly to how a supermassive black hole is abbreviated to SMBH, ultramassive black hole tends to be abbreviated to UMBH. And I've noticed that within papers there actually is a very recent term that's only been around for the past few years or so. In fact, most of the papers that I actually came across on the archive were talking about ultramassive white dwarfs. So very completely a different area of physics, nonetheless still compact objects technically. But yeah, I would recommend being a little bit more careful on the archive than I was when I first looked, and like make sure to include the full term if you want to go and do your own research, which I always highly recommend. Now, a question that you may very validly have is, well, what do astrophysicists consider the border between supermassive black holes and ultramassive black holes? And the answer is, I don't actually know yet. It's a little bit up in the air, mainly because the term is just so new. It's only come about within the past few years with regards to black holes specifically. In general, if you look at a paper on ultramassive black holes, what they will do is make their own definition of what they've considered an ultramassive black hole. In general, that tends to be around 10 billion solar masses, which, yeah, is absolutely humongous. Ton 618 is what I would consider a fantastic example of an ultramassive black hole. Its black hole estimates tend to be, I think the more recent one is around 41 billion solar masses, which, yeah, is extremely large, but there are some older estimates which tend to rank it a little bit higher. Once again, going back onto sort of the models of models things, once you change something or get better constraints on one model, it tends to have a cascade effect, and so I would always recommend looking at the most recent estimates of a model, of a black hole's mass, so as to get most likely the more accurate of all of the measurements that we've got so far. So I'm going to stick with 41 billion solar masses for ton 618. So the reason I make a really big point about this is because when we were looking at the difference between stellar mass and supermassive black holes, there tends to be a more sort of mechanistic divide between the two, where one kind of implies that you need a lot of luminous accretion way beyond like what the original black hole started with, its mass started with. But with ultramassive black holes and supermassive black holes, that tends to be a lot more blurry. There doesn't seem to be a defining thing or like feature or characteristic that splits the two categories apart. It just is more so, well, these ones are much heavier than the rest of them. These are the heaviest ones. We're just going to call them ultramassive from here on. So the divide between the two isn't actually as clear-cut as the stellar and supermassive black holes. And most importantly, there isn't a huge sort of gap in black hole masses between these two. You know, they tend to blur up a little bit more compared to stellar mass and supermassive black holes. I've also seen some people say that Phoenix A is the largest supermassive black hole observed so far. But I'm actually going to have to disagree with that one, mainly because I don't think people have actually checked the sources on Phoenix A. So the most recent estimates, in fact, one of the only estimates that I could find of Phoenix A's black hole, put it in the mass range of around 19 billion solar masses, which is a lot smaller than ton 618. I have seen some people also mention Phoenix A as being the largest supermassive black hole. I've seen the mass of, I think it was 100 billion solar masses floating around as the estimate that people were claiming. And I'm gonna have to disagree with that one, mainly because I checked the sources and I think people have misinterpreted it. The best thing to do when searching up supermassive black holes is, you know, find the actual name of the black hole and go look at papers, the most recent papers. So for Phoenix A, got the actual name up here. The name is going to be 2MassX, so 2MassX, J23444 387-424-3124. I think I've read that correctly. And so if you have a look at papers which have this specific black hole, you will find Phoenix A's black hole and look at the mass estimates for that. And the most recent one that I found estimated the mass to be around 19 billion solar masses, which is a lot less than ton 618. I think the main reason for this false claim is because when I checked the source that actually claims that it was 100 billion solar masses, it didn't actually claim that it was 100 billion solar masses. What it had done is that in the same paragraph, it had mentioned Phoenix A as one of the largest black holes discovered so far, which is true, and it also mentioned the theoretical limit for, I think it was luminous accretion, and I can't remember which way round it is, but you can get different limits based on how the black hole spins and how the accretion disk sort of like accretes onto the black hole, like which way round like the angular momentum is. So like it can change the theoretical limit, which is a bit wild and interesting. But yeah, it can. And for one of those limits, it was 100 billion solar masses. So I think whoever read this article misinterpreted it and assumed that, oh, Phoenix A is at the theoretical mass limit of 100 billion solar masses or so, and like they got that wrong, which is completely understandable. But once again, yeah, I do have to urge people to check their sources. So to summarise this video as best as possible, we know that supermassive black holes can have phases of very luminous accretion, and this is how they will grow their mass. We expect that stellar mass black holes will eventually accrete enough matter up until they match the criterion for a supermassive black hole, which is accretion up to about 100,000 solar masses. And then in terms of the difference between supermassive black holes and ultramassive black holes, we expect that it's basically just a matter of the black hole accreting up to the 10 billion solar mass, and then of course it will just continue accreting and accreting. That kind of left me a little bit disappointed when I was looking at this, because I was really hoping there'd be like a more mechanistic argument for the divide between supermassive and ultramassive black holes, as opposed to it just being, oh, these ones are basically like the creme de la creme of all supermassive black holes and that's it. I felt a little bit annoyed. So I'm really hoping maybe if you guys have like a good idea as to how we could split up these black holes better, I'd really like to hear them in the comments. So anyway, I think that concludes the video. I have yapped far enough for you guys already, and that's basically as much as I know about ultramassive black holes anyways. So I hope you've learned something new, I hope you had fun, but yes, I've yapped enough. It was nice talking to you guys, and I shall see you very soon.